Boa tarde. Ah, é um prazer recomeçar o colóquio do Instituto de Física, o colóquio semanal do Instituto de Física da USP, nesse segundo semestre. Nós temos hoje um convidado do exterior e então nós vamos pedir ao nosso colega, o professor Antônio Figueiredo, para fazer a apresentação desse convidado. Sejam bem-vindos e acompanhem no boletim informativo do Instituto de Física. A gente tem a programação, né, a gente anuncia semanalmente os colóquios, vai ter todas as semanas. Toninho.
Okay, obrigado. So thank you, Paulo, for this introduction to the Institute of Physics colloquium. And for me, it's a really great pleasure to introduce Professor Oleg Lavrentovich from the now Advanced Material and Liquid Crystal Institute from Kent, Ohio. I knew Oleg, if I well remember, since 1984. So a long time ago, we met for the first time, if I well remember, in New York, in one of the International Liquid Crystal Conference. And I was really impressed by the deepness of the work and the research he developed since that time. And since then, we met in different conferences and in different places in this world. And it's really nice that he agreed to give this first colloquium of the semester of the Institute. Well, Oleg received his PhD in 1984, Doctor of Science in 1990 degrees in Physics and Mathematics from the Ukrainian Academy of Science. In 1992, he joined the Liquid Crystal Institute as a senior research fellow. The Liquid Crystal Institute is one of the most important places where the history of liquid crystals is essentially linked. He's also served as the director of this institute from 2003 until 2011. He's fellow of the SPI and American Physical Society, helped visiting appointments at the University of Pierre and Marie Curie, Denis Diderot in France, and many other universities in Europe and other parts of the world. He is now the editor of the Liquid Crystals Review from Taylor and Francis, and associate editor of Soft Matter, member of the different editorial boards, for example, Liquid Crystals, Condensed Matter Physics, Ukrainian Journal of Physics, and also a advisor of the Kent State University SPI student chapter. So, dear Oleg, it's a really big pleasure to me to have you here with us. And please, you can start your talk. Thank you very much, Oleg.
Thank you, Antonio. Thank you for a wonderful introduction. So today I will be talking about some recent research that demonstrates that liquid crystals have potential not only in informational displays, but also in more subtle area, namely by interfacing liquid crystals with living matter, one can gain some level of control over the living matter. The work that I'll be talking today was done by graduate students shown here. Taras graduated last year, and Runa and Moshtaba are current PhD students. And we enjoy collaboration with our colleagues at Kent State, Minko Kim and Sergei Shayanovsky, and also a part of the work was done in collaboration with two groups of theorists, one at Oxford, it's Julia Yeomans, and one here in States at Penn State, Igor Aronson. So I will basically tell you three short stories. But before I go into the details, I need to spend some time introducing the audience to our motivations and basic physics that is in the field. I will start by talking about probably well-known phenomenon of difficulty of moving at low Reynolds number and the famous scallop theorem. Then I will very briefly discuss what are the liquid crystals and how they differ from isotropic fluids such as water. And we'll demonstrate that at low Reynolds number, when viscosity prevails, the dynamics is entirely different in liquid crystals and water. Then I will be talking about how the liquid crystal medium can control individual bacteria that swims. And finally, about polymerized liquid crystals that we use as substrates to grow designed living tissues. So the next slide is this slide is basically our motivation. What you see here is a droplet of water, and in this droplet there is something moving rapidly. Those things are Bacillus subtilis. It's a self-propelled bacterium that moves in water in the search of nutrients. And as you might see, the motion is spectacular and apparently efficient. And the only thing about this motion is that it's mostly chaotic. Even if I would maintain some gradients of nutrients, the bacteria would probably swim towards the nutrients over some time, but then as any gradient, these gradients would disappear and I would get the chaotic motion again. So if I would like to convert this energy into some sustained motion so that I can extract some useful work, I need to communicate to this bacteria which way they are supposed to move. And the problem is that unlike with big animals, we don't have much of communication channels. Visual, audio, and tactile channels are not available most of the time. And so in our work, we decided that this channel of communication might be a liquid crystal environment. And this is basically what my story is about. We replace the normal habitat of micro swimmers with a liquid crystal. So this is the slide with some formula. Don't be scared by those. Those are well-known Navier-Stokes equations, which are nothing else but the Newton's second law that says that the acceleration on the left multiplied by the mass or density is controlled by the forces applied to the system. So the issue is that if you compare the typical expected values of these different terms at different length scales, then you would see that some of the terms become more important than the other. In particular, if the scale of the system is small, then the inertia term on the left-hand side becomes much smaller than the viscosity term. And the ratio of the two, which is called the Reynolds number, becomes extremely small. And if it's small, you can neglect the inertia term and keep only the viscosity term. But if you look at the thing that is left over, then you would realize that there is no time explicitly entering this equation. And that is the problem for propulsion at microscale, as was famously described by Purcell in his paper, with the example of the scallop. So here you see the image of a scallop that might have moved if it were big, by opening and closing its shell. But if it's small, then opening and closing the shell wouldn't help, because of the prevalence of viscosity over inertia. Inertia is not important. And so because of that, Mother Nature needed to work hard to develop modes of swimming that are time irreversible. And one of the simplest is the motion of a corkscrew attached to the head of the bacterium. Here you see the movie from Howard Berg's group of fluorescent bacteria that swims by rotating a helicoidal appendage, the flagellum. And with each half period, this rotation creates a thrust force that propels the bacterium. Of course, it's of interest to develop synthetic version of micro swimmers, and many people are trying to do that. But again, the scallop theorem tells you that it's not that simple. And for example, a simple sphere could not easily propel itself. Here you see the best achievable, theoretically at least, configurations. One is with 3 joint spheres, and another one is with 2 spheres that are connected by the rod along which the material can flow back and forth. So those are the simplest swimmers that can be created artificially that are based on spheres. So the main result of my first part is that I will demonstrate you that if one replaces the isotropic fluid with a liquid crystal, then the system might be much simpler. It suffices to have a sphere, a spherical droplet, to produce a good swimmer. So a few words about liquid crystals. Liquid crystals, and we are dealing with the simplest nematic type of the liquid crystals, are fluids in which the molecules are aligned parallel to some common direction called the director. Because of this orientational order, liquid crystals feature some elasticity. If one would like to depart from the uniform state and create some deformation, like shown in the center of the slide, then it means overcoming some elastic energy. And this elastic energy is the integral of the director gradients. And if you look at this formula, you would realize that the result of this integration would be linear in the size of the system and proportional to some elastic constant. Anisotropic interactions in the bulk also feature at the surfaces. Surface always imposes some preferred orientation on the director, and if one needs to change that orientation, that again means overcoming some resistance. And obviously the elastic, the anchoring energy, as we call it, associated with the surface alignment is proportional to the area over which we would like to change the orientation. And so if you look now at these 2 expressions, you would realize that they form the characteristic length scale. So if the size of the deformed system is larger than K divided by W, the anchoring length, then it will be the prevalence of surfaces. Although it might be counterintuitive, but it is the fact that surfaces win at large scales. And if the scale is smaller than this K over W, then the bulk elasticity wins. So let's consider how it applies to a very simple problem. And we have the little droplets, and at the surface of the droplet, the liquid crystal director wants to be perpendicular to the surface, but the overall nematic cell is aligned uniformly. So what would happen? If the particle is small, smaller than this K over W, then it's the bulk elasticity that wins, and this elasticity would like to keep the director field uniform. But if the particle is large, then the surface anchoring should be satisfied. And one solution is to have the director field striking the interface perpendicularly. And if you just draw a picture, one of the solutions might be this Saturn ring configuration shown here. So it's a destination loop that embraces the equatorial plane of the droplet. A little bit more energetically stable solution is the one shown on the right. This is obtained from the Saturn ring by shrinking the effect loop into a point. And here I show the resulting point effect on the right-hand side, or it can be also shifted to the left. And we call this defect a hyperbolic hedgehog. So here you can see a movie of what the droplet with such a configuration with the hyperbolic hedgehog does when you look at it under the microscope closely. You see Brownian motion. The only difference from the Brownian motion in isotropic fluid is that the trajectories are slightly elongated along the director. And it comes as no surprise because swimming along the director or moving along the director is meeting smaller viscous resistance. But the main point, as in any Brownian motion, is that over time, there is no net displacement. The particle just moves around the position and its original position, and that's it. So the question is, what would happen if instead of this passive droplet, we use an active droplet? And active, I mean just a droplet of water in which we place swimming bacteria that convert chemical energy of nutrients into some mechanical motion. So the next slide shows a dramatic difference from the previous Brownian motion. What you see here is that this droplet filled with bacteria moves in one direction. You can measure how much it moves on the right-hand side. You see that along the horizontal axis, it moves steadily, and in the perpendicular direction, the displacement fluctuates about zero, but never gains any useful propulsion. So this is a dramatic effect because it tells you that once you have an active droplet instead of a passive, and once you place it in the liquid crystal, it can move itself over long distances as long as the bacteria are active. So the experiment can be modified slightly. If I use a shallow cell, then I can create a Saturn ring, which is held by the two confinement plates. And if it's a Saturn ring, as you might see at the beginning of the movie, the droplet doesn't want to move much. It only moves when the Saturn ring shrinks into a point, as you see now, and after that, the droplet moves to the right-hand side. It is important to realize that this phenomenon of propulsion occurs only when the medium is nematic. If it's not a liquid crystal melted into the isotropic phase, as just happened in this movie, then the motion stops. So on the right-hand side, you see the temperature goes up, and then when it reaches the so-called clearing temperature, the nematic melts into the isotropic fluid, and at that moment, the propulsion stops. So to understand what is going on with the dynamics, we modify the experiments by placing fluorescent particles inside the droplet. And here you see how they behave. They move around, and they move around simply because they are pushed by the bacteria. You don't see the bacteria in this movie because the bacteria are not fluorescently labeled. And you might see a rather strong motion, especially near the surface of the droplet. So what you see here is the interior of this water droplet with bacteria. Then if you average the trajectory of fluorescent particles inside and outside the droplet, you would realize that inside it's totally chaotic. There is no preferred direction of motion, no preferred speed. It's just chaotic motion. But on the right-hand side, in the liquid crystal, if you repeat the same experiment and measure the trajectories of fluorescent particles, you see that the flows are rectified. Namely, there are much more arrows looking, apologies, and let me come back, moving from right to left than in the opposite direction. And this tells you that the chaotic motion from the inside of the droplet is being transferred to the outside, and then because of the symmetry of the director deformations, it is being rectified. And the next few slides help to substantiate what I just said. So consider a vertical cross-section of the cell. So the director is aligned perpendicularly to the surface of the droplet, and then it has to reorient to become parallel to the glass plates at the top and glass plate at the bottom. So suppose that the internal motion of bacteria causes the shift of the droplet, let's say, to the left. The director outside the droplet has to react somehow, and you see here that I have changed the configuration slightly just because the director has to follow the entering conditions. Now consider the jump to the right. Again, the director has to accommodate, but now this direction is much easier because the director becomes more aligned overall. And here I just show overlap jumps to the left and to the right. These two jumps have different director configurations. As the result, they have different viscous resistance to the shift of the droplet. And this difference creates a propulsive force that moves the droplet to the right-hand side. Of course, this propulsive force is being countered by the viscous drag, and comparing the two, you arrive at the conclusion that the velocity must be proportional to the difference in the effective viscosity for the jumps to the right and to the left. And since jumps to the right are easier because the director is more uniform, shown in red here, that produces propulsion with the hedgehog leading the way. So once you understand this more or less in terms of physics, you can play with different engineering. Here we pattern the liquid crystal in the shape of circular trajectories, and the droplets follow these trajectories because they would like to swim parallel to the director. You can also create a situation when the droplet would stop at some points, like a bus stop. And this is done by templating topological defects, such as this one. So the droplet is attracted to the center, and once it reaches the center, it's happy there because the boundary conditions are satisfying the anchoring. With the liquid crystal environment, as we all know from liquid crystal displays, you can do a lot by applying electric field. In particular, you can change the overall direction of motion, or you can change the speed with which the particle is moving simply by expanding the hedgehog into the Saturn ring. And as you do so, the velocity goes to zero. So this little example shows that nematic environment offers a distinct opportunity for microscale propulsion, which is based on the interplay between the orientational order and hydrodynamics. And in this particular case, we can say that we can control the active drop by the director patterns and the electric field. So the next story is whether we can control not just the droplet with thousands of bacteria inside, but can we control individual bacteria? And for that, we need to have a different type of Lick crystal. This is the lyotropic harmonic Lick crystal, which represents water dispersions of disc-like molecules. So on the right-hand side, you see how the molecules aggregate into long cylindrical bodies, and when the concentration is high enough, these cylindrical bodies aggregate, align parallel to each other. And since the environment is water, it's not toxic to the bacteria. The harmonic molecules do not have aliphatic tails, and because of that, they are also not toxic. And if you place the bacteria in such an environment, then first of all, you can clearly see how the bacterium swings, because the birefringence of the nematic allows you to visualize this helicoidal tail. Otherwise, in isotopic fluid, if you don't fluorescently label the bacteria, you wouldn't see this motion. For physics, it's important to kind of represent the swimming bacterium with the simplest object possible, and that would be an ellipsoid with two forces. One is the propulsive force, and another one is drag force, which is of the same amplitude but opposite direction. According to the third Newton's law, since there is no external force applied to the bacterium when it swims, this swimming should be force-free. So these two forces should exactly cancel each other. And this little image of the ellipsoid with two forces looking outward is important to keep in mind for the rest of the presentation. So if you create a uniformly aligned cell and place the bacteria in this lyotropic Lick crystal, you would see that the bacteria kind of feel the presence of oriented aggregates, and they swim parallel to the direction of the orientation of the surrounding Lick crystal. However, when you look at this picture, you would notice that the swimming to the left is equally probable as swimming to the right. And that simply means that there is no useful work that you could extract from this motion. And our goal is to make the swimming polar, to have this bacteria move from point A to point B, but not from point B to point A. And so we started to play with the gradients of the director field. We started to try to design different configurations. And here you see two examples when nothing works, because if we create a circular pattern on the director, the bacteria move clockwise and anti-clockwise, and again, there is no useful work. If you create a radial configuration, the same problem. The bacteria go in and out, but not much of polarity there. But then if you have your structures of mixed geometry between radial and circular, make it spiral, you would immediately see the result that creates polar circulation. Here, all the bacteria move counterclockwise, and I can show you some other movies when there are many clusters like that, and all of them move in the same direction. So the physics is, in fact, very simple. If you imagine the bacteria as this little ellipsoids with two forces, and if you imagine them being aligned by the director field, then you should consider what happens in the neighborhood between these two closely located bacteria. You see that the two forces are canceling each other in the horizontal direction, but they cannot cancel each other in the vertical direction. And this creates a net force. And if you repeat the consideration for other locations, you would realize that this red net force forms clockwise circulation. You can put it in algebraic form using the expression for the net force written here and first considered by Simha and Ramaswamy. And you can solve the equation of how this force competes with the drag force, and you would arrive at the expression for the velocity that changes along the radial distance from the defect. Here, this theoretical prediction is shown in red. And it's more or less the same what we see in the experiment. The bacteria move along the azimuthal direction. There is no component along the radial direction. It's 0 here. And it explains the active flow in counterclockwise direction. So the question is, I mentioned that the bacteria are close enough. The question is, how close should they be to feel each other? And the next experiment shows you how the scenario changes when you go from very few bacteria, shown in this corner. The first move is just 4 or 5 of them, and they move in this pattern. But since they are not interacting, they only listen to the director field. They go to the center and then escape. If you increase the concentration of bacteria, then you start to see some collective behavior. And the bacteria starts to form some little loops. And as the concentration goes up, then you see the onset of collective behavior. They now do not listen to the director field that much. They create loops that circulate. And here I show an example when the design was to force them to move clockwise. And the result is easy to understand from this slide. At the bottom, I show 2 distant bacteria. They don't interact and they don't feel each other. And there is no collective behavior. They just move along the director field. But if the concentration is higher, as in the top part, then the water jets that the bacteria create around themselves when they swim, because the rotation of the flagellum creates the outburst of the medium around them, then these hydrodynamic interactions produce the net force, as we saw previously, and this net force has a proper clockwise or counterclockwise orientation. And it also, when the angle of spiral is different from 45 degrees, it also creates a radial direction. And here the radial direction is towards the center. So by designing different spirals, we can expand the swirls of the bacteria or contract them. But instead of talking about that, I would like to show the last slide from this portion, which is what we wanted from the beginning. We wanted the bacteria to move from point A to point B and not in the opposite direction. And we achieved that. You can compare it with the isotropic case. It's totally different regime. And now we can use it. For example, we can ask the bacteria to carry some cargo. Here you see a small colloidal particle that is being transported from left to right by the polar jet of the bacteria. So I intentionally didn't show you the director field so that you can have time to think what might be the director field. Now I think you had enough time, so I can show you this director field. It's a kind of periodic splay and then deformation that creates the jet of the bacteria. There are no walls here. The vertical direction has no restrictions for the bacteria to move up or down. But as you might see, they simply don't want to do that because that means they would swim perpendicularly to the director, and they don't want to do that. So the second conclusion is that an isotropic Lake crystal environment offer a mechanism of the microscale proportion in a particular direction for individual bacteria. And by patterning this Lake crystal cell, we can control the trajectories and the special distribution of microswimmers. And we can create circular and linear flows and at the end even force the bacteria to carry some cargo. And the last part of this talk is also about liquid crystals, but now these liquid crystals are not the medium, they're a substrate. So the liquid crystal is polymerized, we call it liquid crystal elastomer, and then on top of this polymerized liquid crystal, we place living cells, and we want to guide these cells to particular patterns. First, let me explain why it's of interest. This is the picture that inspired us. In 2017, there was a Nature paper that described that epithelium is actually an emetic liquid crystal because the elongated cells are forming orientationally ordered patterns. And what was especially interesting was that there are defects in this pattern. And one particular type of defect shown with red label 1/2, which is called positive 1/2 disclination, plays an important biological role. Namely, at the core of this defect happens apoptosis. Namely, the dead cells are being extracted or expelled from the tissue precisely at the course of these defects. So when we saw this thing, we realized that, okay, it's very nice, but what if we would like to tell the tissue where to create this defect so that we kind of know at which location the dead cells will be most efficiently ejected. Maybe it's of some interest for distant future cancer applications. So we would like to grow a tissue in which the pattern and defect is not just random, but controlled by us. And for that, we are using the liquid crystal elastomers that are substrate, serving as substrate for the tissue. Our living cells are human dermal fibroblasts, shown here. They are part of a normal skin, and they are relatively large, 100 micrometers in length. And the substrate is shown here. So this is the image of the liquid crystal elastomer, which is the liquid crystal polymerized. And then prior to polymerization, we align this liquid crystal, and then we drop a droplet of water on the surface. And what happens is that this polymer swells in presence of water, and this swelling creates the grains elevations that you see here. These elevations are aligned along the direction of orientation of the liquid crystal, and the living cells are very sensitive to elevations on the order of few tenths of nanometers, and we use this to guide their growth. The next slide is kind of complicated, but you see the top view of the cell. The substrate is this aligned liquid crystal. You can see the little ticks at the background, very small, maybe a millimeter on your screen, and then large bodies that are elongated and aligned more or less horizontal. These bright circular formations are the cells that are still in water, and they are sedimenting on the substrate. And once they sediment, they convert themselves from spheres into elongated cells. And these cells move back and forth and test the environment. As you might see here, they realize that the environment is anisotropic, and they align themselves parallel to the substrate directionality. The next slide shows you the net result of this alignment. It requires some 10 days to grow the confluent tissue, meaning that everything is filled with the cells. But the result is that the cells are aligned by the substrate. And now, instead of using the uniform pattern, we create patterns with defects, because that's what we wanted from the start. We wanted to have the patterns of the tissue. And here I show the pattern that has so-called plus and minus 1/2 defect. And as you might see in the movie, the growing tissue totally reproduces the pattern that we pre-engineered. There is an interesting stuff that I'm not going to comment much, that the cells prefer the course of positive defects than the negative, and the confirmation of that is that their density is much higher near the positive defects than near the negative defects. But there is also another thing. If you look over time at this defect course, in particular +1 defect course, you would notice that the course splits into 2 1/2 disclinations. And with time, these disclinations move away from each other. So then we repeated the experiment with a similar pattern, but now the +1 defect has a radial configuration rather than circular. And you see that the tissue grows and forms the pattern that we wanted, and the +1 defect is of radial symmetry. But then if you compare the splitting behavior, you would see a dramatic difference. In the first movie, the course of the defects try to separate away from each other. In the second movie, with time, they did the opposite. They tried to come closer to each other. And the qualitative explanation is again based on these ellipsoids. Why do I show ellipsoids for cells when I use them for bacteria? Because it's the same thing from the physics point of view. Each cell is propelling itself, but it's a force-free propulsion. So the two forces must cancel each other. And if I place the cells on the orientational pattern, then the geometry of this pattern would dictate which way the active force is oriented. If they are located in the originally circular pattern, then as you might see here, the net force is outwards towards the periphery. So this force will separate the course of the defect here and this one farther away from each other. But if the initial structure is radial, then the net force will be towards the center and the defects will approach each other. So here you see a little theoretical analysis of the balance between elasticity that wants the defects to split into smaller strengths, which is very familiar for those who did dislocations in solids. The smaller Barger's vector, the smaller is the energy of a dislocation. So the same thing is here. The elastic energy drops when you have a smaller strength of the defect. And there is also anchoring, because when I separate the course of the defects, then the orientation in the tissue is no longer the same as was pre-patterned at the substrate. So the long story short, the passive forces, namely anchoring and elasticity, works similarly in these two cases of the radial configuration and the circular configuration. And the only difference that brings these two cases apart is the active force. In the left case, it wants to move the defects closer to each other. On the right-hand side, it's just the opposite. And so now you balance the forces, you go through a simple quadratic equation, and from that equation and experimental data, you extract two nice quantities. You extract the elasticity constant of the tissue, which is 5 nanonewtons, some 3 orders of magnitude higher than the typical Cramp constant in Lick crystals. And you can also estimate the anchoring strengths, the strengths with which the cells follow the substrate orientation. So the last conclusion is that Lick crystals prepared as elastomer coatings can also be interfaced with living matter. And in this particular case, they can control human dermal fibroblasts. And by studying the patterns, we can extract some information about the properties of the tissues. That's all. I think that these three examples demonstrated the potential utility of liquid crystals in bio applications, and there is still a lot of things that could be done in understanding many mechanisms that are behind this phenomenon. Thank you very much for your attention.
Thank you very much, Oleg. Very, very nice talk. And it's clear that liquid crystals not only displays, we have a lot of things to do with it. So I open for people that would like to make questions. You can make questions in Portuguese. We can translate for you if you want. And let me start with one question here. Did you think about to put a long-range interaction between these bacteria? For example, working with magnetic bacteria? What would expect?
No, we did not. So the limiting factor was the nature of bacteria. So we used Bacillus satilis, and that was a very nice type of bacterium because it was strong enough to propel itself through the liquid crystal. I know also that E. coli, but very specially prepared E. coli, kind of E. coli on steroids, that is strong enough to move through the liquid crystal. And many others are not simply, they are either kind of toxic and dangerous, or in the case of magnetic, from what I understood from literature, they are not kind of big enough, strong enough to move themselves through the liquid crystal, although it would be a very interesting topic if one could combine magnetic and liquid crystals.
But when you put a long-range interaction between particles, probably the only thing that would change, I don't know, I'm thinking now, would be the minimum concentration of bacteria to have this collective behavior. Or you
I agree with you.
Yeah.
That's true, because in our case, you might see that we need distances about 20, 30 micrometers between the bacteria so that they start to feel the water jets of each other. In the magnetic case, it might be longer distance. So it might be an interesting topic to study, but we didn't.
Okay. Please, more questions. Is there a question? Do you have questions in the YouTube? Who is controlling the YouTube? Paulo.
I am. There's no question there. If there is a question, I'll raise my hand.
Okay, there is one question here from André Vieira. I will unmute.
Okay.
Oh.
Hi, thanks for the nice talk. I would have a question about the second topic. You showed us unipolar linear motion, but what about bipolar but organized motion in which opposite moving bacteria would move in distinct lanes? Have you considered that kind of thing, or would that be an interesting thing to consider?
Could you repeat the last part of the question, because I didn't understand what the question was?
Okay. I was asking about bipolar but organized movements in which opposite moving bacteria would move in organized lanes, in different lanes, but for instance, one lane of bacteria going to the right and one lane of bacteria going to the left, but organized.
Yeah, I understand.
not
Yeah, I understand. So this movie shows that they are kind of mixed. But then if you go to the last movie of this section, then if I just show you one jet. Let me do this. Yeah, here. So yeah, we can create the lanes in which in one lane all the bacteria move to the right, and in the next all the bacteria move to the left. That's possible. We in fact I show you on the one lane, but if you read this paper, then you would see that we can create many channels. In this particular paper, we describe that all of them move in the same direction, and if a bacterium wants to escape, it's simply being thrown away to the neighboring lane and again moves from left to right. Here you see in this movie, this guy, yeah, this bright at the bottom, it wants to escape, and in principle, if it escapes, it's being carried away to the next lane, and there it can go whatever we design. So in principle, it's possible, yes.
Okay, thank you.
Another question, Oleg. When you made the experiment with a allotropic liquid crystal, you used chromonic liquid crystals. And what would you expect if you use a nematic, usual nematic potassium laurate decanal water, for example, that presents the three nematic phases, biaxial also? You would expect a new phenomena, new movements when you have a phase transition, for example, as a function of the temperature from a nematic calamitic to a biaxial. What would you expect, for example?
Yeah, it would be very interesting. We didn't try it simply because we are afraid that the surfactant nature of this type of allotropic liquid crystals might simply kill the bacteria. So that's why we didn't do it.
Okay.
But if you would find that they are not killing them, then it would be a very interesting subject. We simply didn't work with potassium laurate and this type of a system. So.
Yeah, I understand. There is a question, Paulo.
Yeah, again, very interesting talk. I'm not from the field, so I would have actually two maybe naive questions. One is about this slide that you have on this colloidal transport by bacterial jets. In what kind of situation would this be specific, especially interesting? Is it possible to create some, unusual fluid by transporting such particles with the bacteria? That's one question. The other one is, so you said that you want to generate work by bacteria, right? Are you talking about some kind of motor, bacterial motor, where regular, thermodynamic questions would be important?
Yeah, you can answer this question at a very different level. So this movie that you referred to is kind of an answer to probably both questions. So yeah, in terms of what kind of practical applications it might lead to, remains to be seen. One can say, okay, for example, I can force the bacteria to start a chemical reaction. So if this is the colloidal droplet with some chemical, and there is a spot with another chemical at the end of this trajectory, then the bacteria would push the two together, and I would start the micro-scale chemical reaction. Regarding the useful work, again, this movie is exactly that. The colloidal particle in this movie moves from left to right, and this is the useful work. The useful, of course, here is in the quotation, you know, if you can use it, but it is a directional work. It's not a random Brownian motion, left and right. It's really a deterministic motion of the particle. And in principle, yeah, we thought about the rotational geometries, and you might see in this movie that I showed, yeah, this movie. If you put a post in the center of this pattern, then you can rotate this post, and the bacteria would create a rotor that per your design can be either clockwise or counterclockwise.
Okay, still in this movie you are showing to us, in principle, I would expect that the bacteria would come together and accumulate in the center, but they do not do that. They go almost in a circle. But
yes, that's right. Moreover, we can control what you just said. We can make them expand, and we can make them contract. And I left these slides outside. So here is the pattern. If the spiral angle is small, then this active force is having a radial component that brings the bacteria to the center. If it's 45 degrees, theoretically, the radial component is 0, and is 0, and there is only azimuthal component, so that they do not contract, they do not expand, they behave as you said. Yeah. But if the spiral angle is huge, then they are expelled to the periphery. And the next slide shows the experiments. So this is 45 degrees. It's a very stable circulation. But if it's, let's say, 10 degrees or 25, you can see that the radius of the swirl is much smaller. And if it's going to 80 degrees, it expands to the periphery. So yeah, there is this interesting.
Very nice, really nice. It should be like a model for the expansion of the universe.
Well, at least small portion of the universe.
Okay. Is there any more questions? No, I don't see. If not, let us thank Oleg again. Thank you really very, very much. It was a pleasure to have you here with us.
Thank you.
I hope to see you soon somewhere.
Thank you all. Thank you for your
Thank
interest.
you very much. Thank you.
Thank you. Bye-bye.
Bye-bye.